All right, let's get started. So we left off with testing doubles last time. We didn't finish the slides, so let's wrap those up and then get into today's content. So we left off introducing what unit testing was and then talked about testing strings. Never use equal to test strings, and we use the equals method instead whenever we want to compare two strings. So with doubles, there are concerns with testing doubles as well, so let's talk about those. Punchline is going to be don't use equal. And this is the most common error that we're seeing in office hours and Piazza is students testing their doubles the wrong way, which is on me because I didn't get to these slides on Wednesday. So let's get to these and get you all understanding why this test fails. So if you go into the examples repo, you can find this test, you can verify yourself, you can run this test, and it will fail. Now we have 0.3 equal 0.1 times 3.0. 0.1 times 3.0, we would expect to evaluate to 0.3. We're going to check to make sure it evaluates to what we want it to evaluate to. And this test fails. The computer says, nah, that's not equal 0.3. The problem is 0.1 times 0.3, according to the computer, is not or 3.0, is not 0.3, it's this value. I ran this, printed it to the screen in my IntelliJ, and this is the exact value that I get when I multiply 0.1 times 3.0. It's going to be this value, which is pretty much 0.3. We, as humans, would all consider that 0.3. It's close enough. That 4 way out there, like 12 decimal places out, we don't really care about, but the computer does. These are not equivalent values. They're not exactly equal bit for bit. So to the computer, these are not the same value. This is not 0.3. Since it's not 0.3, this evaluates to false, and your test fails. If you're getting your test failed a correct solution in Autolab, like 90% of the time when we're getting that as a symptom, this is going to be the issue, again, because I didn't get to it on Wednesday. So you jump into the homework after Wednesday, and then, of course, I didn't get far enough in lecture to prepare you for that one. But this is an issue. You can't use equal to compare two doubles. Never use equal to compare two doubles. Never use equal to compare two strings, at least in Java, with the strings, in any language I've used for doubles. So the reason this is the case is that a double is represented in 64 bits. Now, we're not too concerned about the actual structure of a double in this class. I have the image up here, the diagram here. I'll briefly explain it. The fraction part is the precision of the value. So this is basically like scientific notation where the fraction is 1 point the fraction value. And then that's raised to 2 to the power of the exponent, this 11-bit exponent value, and then 1 bit for the sign, whether it's positive or negative. So it's effectively scientific notation, but in binary. You'll learn all about that in much more detail in 220, CC 220. For now, in 116, what we need to understand is that 64 bits is less than infinity bits. This is a finite representation, a finite number of bits to represent a value. So when we represent values in decimal, if we want to represent, say, the value 1/3 as a fraction, or in scientific notation in our case here, we have to write 0.333, or in scientific notation 3.333, I guess, since I mentioned that. 3333, and eventually we're going to get sick of writing 3s, or we're going to run out of memory in our computer to write 3s. Eventually we're going to stop writing 3s before we reach infinity 3s. We're going to stop before then. And when we do stop, we're not getting exactly 1/3 in that representation. We can't exactly represent 1/3 as a decimal value like this. Can't do it. So the way we represent binary values and doubles in our case here is a very similar way. Similar to how 0.333, this is 3 tenths plus 3 hundredths plus 3 thousandths plus 3 10,000ths, or rather 3 over 10 to the 1, 3 over 10 to the 2, 3 over 10 to the 3, 3 over 10 to the 4. We represent binary the same way. 0.11 in binary is 1 over 2 to the 1, 1 over 2 to the 2, or 1/2 plus 1/4, so 3/4. So 0.11 in binary is the value 3/4. So we're representing things in a very similar way in binary as we do in decimal. Of course, the computer only speaks binary, so we have to represent everything in binary. And there are certain values like 0.1 in decimal, not 1/2, but 1/10. 0.1 in decimal can't be represented as the sum of fractions of powers of 2. To represent 0.1 or 1/10 in decimal, we need the binary value 0.000110011 repeating forever. That sequence repeats out to infinity to exactly represent the value 1/10 in binary. At some point, 64 bits just isn't enough, and the computer has to truncate our value. So we can't store 0.1 exactly in the computer, and that difference is what we call a truncation error. Since we can't represent exactly 0.1, the difference between this value after we run out of bits in our double representation are 64 bits. And this is going to be our truncation error, and that's what's causing that test from the previous slide to fail. So 64 bits just isn't enough. A lot of our values are going to be slightly off of what we expect them to be. So we have a solution to this. Whenever we compare two doubles for equality, we're going to allow some tolerance. We're going to say as long as these two doubles are within some small value of each other, we're going to call it good enough. We're going to say those doubles are equal. So we're going to do that by taking the difference of the values, take the absolute value of that to get the magnitude of the difference, and make sure that's less than some small value that we define. We have a little bit of extra notation here. Oh, I missed that question last time. I have a little bit of new notation here I want to talk about. I'm just sprinkling in some new notation, new stuff here. Private final double epsilon with all capitals. This is a constant in Java. This is like saying const in JavaScript with this final here. Final means you assign the value one time and you can never change the value of epsilon. So this is how we're defining a constant in Java. And we have private here as well. I believe the first time we've seen private. Private means that we can only access this value from inside this class. Can't access it from anywhere outside the code in this class, in the testing class. So we don't want anybody to access this. This is just to help our methods inside this class. So we don't need anybody outside this class to be able to access it. So we make it private. Private final. This is a private constant. Wish they just used const or constant here instead of final. And then double the type of the variable. And then by convention, this isn't required by the language, but it will be highly encouraged by all of your peers. I mean, like when you graduate and you're working in a team of developers, they're going to require this. That constants are all capital letters. This is different across languages. In Java, the convention is all capital letters for a constant value. So whenever we use a value, down here when I'm using this value and I see something with all capital letters, I know that's a constant value. I don't have to go look up at the definition and check if it's final. I know it's a constant because of its name being all capitals. And that's one way that developers communicate to each other. It's one way I communicate to anybody reading this code. Epsilon is a constant and should never be changing. Don't try to change it. Some of you will just put something like 0.001 right here without a constant. It's fine. I'm not going to get mad at you for that. But I want to show you a better way of setting it up. And I'm going to choose a value for epsilon, how much tolerance I want to allow. In this case, 0.001, as long as my two doubles are within that, I'm going to call them good. I'm going to call them basically equivalent and pass my test. The choice of this value can be different based on your actual application. But there are two rules of thumb to follow for this. The value should be large enough to allow for truncation errors. So any truncation error that can occur, this value should be large enough to make sure that those truncation errors don't cause a failure in your test cases. We don't care about those truncation errors, let's just ignore them. Now, the truncation error that we saw, it was ridiculously small, but sometimes you can have very large truncation errors, fairly large, I shouldn't say very large, but fairly large truncation errors. In some cases, they can get very large if you're not too careful. Because these can compound. So for example, your average method, actually that's a bad example because that's not multiplication, but if you're multiplying a bunch of values in a loop and you're constantly multiplying, those truncation errors can compound and get fairly large that way. If you're just doing one multiplication, one arithmetic operation, you're not going to get too big of truncation errors, but if they start compounding, they can add up to be something fairly significant. So you don't want to set epsilon to something like e to the negative 15 or something. You want it to be fairly large to make sure you're allowing for truncation errors to exist. But it needs to be small enough to not interfere with the logic of your code. So if you have too large of an epsilon, then it's going to start interfering with the logic, and you're going to start accepting incorrect code as correct. So for example, if epsilon was 10, and I have a method that says that's supposed to return 2, and it returns 11 instead, my test case is going to be like, hey, you're within 10. That's good. You're doing a good job. Pass this code. So you don't want that. You got to be careful to not make these too large as well. And like I said, it depends on application. I used to run in Scala. Maybe someday it'll be a Java assignment too. Not this semester though. I would have an assignment called Pale Blue Dot, which worked with locations on Earth, on the whole globe. And we were computing distances between cities. And in that application, if you're off by a full kilometer when you're talking about distances between cities, it was fine. So our epsilons were usually 1.0 for that application. Because if you're off by a kilometer for that, we were okay with that. And there was a lot of trig, a lot of math going on that did compound truncation errors. Sometimes the latitudes and longitudes didn't have enough significant figures even to get that much precision. So we allowed 1.0 kilometers. So it depends on your application. You want to think about what a good epsilon is. A good starting point, I usually start with something like 0.001 is usually good enough for our purposes. But if that's if we're dealing with, I don't want to go down that road. I was going to say, if we're dealing with money, you got to think of this. This is a tenth of a penny. Is that good enough? Should you go further? If you're dealing with money, you definitely don't want to have an epsilon of 0.01. That's a full penny. You don't want to be able to be a penny off in all your calculations. Eventually, you're going to lose a lot of money if you're always giving the other side a full penny. That'll add up a lot. But just thinking about what your epsilon can be. And if you're writing production code that deals with money, there's a lot of other things you need to worry about besides your epsilon, like that, like not using doubles at all. But anyway, your choice of epsilon is important. Make sure it's not too big, not too large. Make sure it's just right. And finally, don't forget your absolute value. I see this every once in a while in office hours. A student will forget that absolute value, and all their code will break. Not code will break, but their test won't be failing incorrect solutions in AutoLab if that absolute value isn't there. So we're not concerned with just the difference between the values, with the actual difference between these two values. We're concerned with the magnitude of the difference. So for example, if D1 is less than D2, you're going to get a negative number, and any negative number, even if it's negative 1,000,000, it's going to be less than whatever you chose for epsilon, because you're always choosing a positive value for epsilon. So don't forget your absolute value. I see this when students are cut and pasting this, and somewhere along the lines they lose their absolute value for some reason. I don't know how they even do it, but or they're just typing this from memory and they forget to type the absolute value. They have all kinds of bugs in their code, in their testing. Don't forget that absolute value. It's very important. The magnitude of the difference should be less than epsilon. That's going to check if these doubles are within epsilon of each other. And the name epsilon, you can name these whatever you want. I typically stick with epsilon. I get this from math. You've probably seen this in calc or pre-calc or wherever. A small value in epsilon in mathematics, They usually use epsilon, so I just kind of stole that from mathematic notation. And notice that I wrote this in a separate method. I recommend you do the same thing. I strongly recommend this. I don't think I ever recommend anything. I always strongly recommend. But I recommend doing it this way, where you write a separate method to compare your doubles and then call that method whenever you need it. It keeps your code a lot cleaner, and more importantly, it reduces the possibility of typos. So if you write this once, or let's be real, you're going to copy it from the slides or from the examples repo and put this in your code, just write that method one time and just use it over and over and over. I've written this method roughly twice, well, multiple times, but once for Scala and now once for Java. And actually, I think Paul wrote this one, so I might not even wrote this. And then I just copy it wherever I need it. I write it once, I write it well, I have my epsilon very clearly labeled there so I can update my epsilon for different applications, and then I'm never writing it again. I just call the method. If you're copying and pasting this line like a lot of students do, you'll often get copy-paste errors. I'll see a very common error is to just paste this line over and over and over again, but not update the variables properly. So they'll have like D1, D2, and then they want to compare D3 and D4, but they'll forget to update the variables, and they'll be comparing the wrong values, and they'll be like, why doesn't my code work? Just write the method once, and then call it whenever you need it, and that'll help you out writing your tests. And notice this is a helper method, so it's just helping me write my tests. It's helping me to organize my code. This is not a test itself, so I just don't give it the test annotation. So this method is in my testing class, but I didn't say @test here because I don't want JUnit to look at this as a test. It won't even be able to because it takes parameters, and tests shouldn't be taking parameters. So in @test here, we don't want that. We just say, don't look at this method. This is my actual test that I want JUnit to look at. And then in this test, I'll call the compare doubles method, which actually has my assert in it. And I don't want JUnit looking at my compare doubles method. So I just don't annotate it with @test. So be careful where your @tests are. This does have a lot of meaning where you have @test and where you don't have @test. All right, any questions on testing doubles? Yeah, epsilon, it's just a Greek letter. In math, they just use the symbol for epsilon. Yeah.
Let's say I'm multiplying pi with a number, and the tolerance is like, like how would I test this function? So I want to multiply it. Then do I call the function, compare doubles, and then use
Mm-hmm. Yes. Yeah, so you would call compare doubles, and the two arguments that you give it, one of them will be whatever your method returned. So for average, the one that we're going to test with doubles, you're going to create an array list, put some doubles in it, do the math either in your head or a calculator or whatever, figure out what you expect that to return. Call your average method, grab the return value, and then take your expected value that you expect it to return, and those are your two arguments to compare doubles. So you're calling average, and if you want, you can do that in a line here. Call average, and put the value, hard code the value that you expect that call to return.
Okay,
and those are your two inputs to compare doubles. And then the method will do the rest. It'll make sure that those two values are good within epsilon. Yep, no problem. Talk about testing in CC 116 a little bit. As we're getting into task 1, you're starting to see this. When your tests are tested in Autolab, you see a whole bunch of feedback. I have some right up on the homework handout itself. There's some in in Piazza, in Autolab too, and the feedback in Autolab itself. I want to also cover this in lecture and make sure we're all on the same page with what that feedback means and what's going on in Autolab. So when you submit your tests in Autolab is going to test your tests. It's going to do this in two separate phases. The first one is going to run your code against a correct solution. There's a correct solution, a known correct solution in Autolab, and it's going to run your tests against that solution. And your tests need to pass that solution. Your tests need to say, yep, that's a correct solution. We're all good on this one. Right now, the questions that we're getting about the homework are mostly about that. Your test failed a correct solution. And a lot of it is 90% of the time right now, it's that you're comparing doubles with equal. Again, I didn't get to it in lecture in time on Wednesday, so anybody who started the homework was usually run into that just because I didn't prepare you for it. So once we're beyond that, you should start seeing your test pass a correct solution. That means everything's good with your test cases in the sense that you're testing the right things in the right ways. So that gets past the first step. That means you're not explicitly testing the wrong thing. Your tests aren't completely broken from square one. Then your tests are going to be ran against multiple incorrect solutions. For these incorrect solutions, your tests need to fail each one of them. So we want your tests to be good enough, thorough enough, robust enough to be able to say, no, all these are wrong. All those incorrect solutions are incorrect. Your test should be able to distinguish between those. Your tests need to be able to distinguish between correct and incorrect. So this is how we're doing it in Autolab. And when you're running your tests, when you're running your code, and you should, of course, run your code against your tests in IntelliJ, when you're running your code against your tests, all it takes is one test case to fail, and your whole code fails. You fail that test, you fail that test class, which it does demand perfection. We have to pass all our tests. If you write a test case, your code better pass that test case. This is generally how we want bug-free code. On the other side of that, when you're writing your tests and trying to get rid of these incorrect solutions, all you need is one test case to fail. If any one test case fails an incorrect solution, you're good. You've said, nope, that is an incorrect solution because here's my one test case. That solution passed my 100 other test cases that I have, but don't worry, I got this one test case that it fails, therefore that's an incorrect solution, and then your code moves on and says, okay, Autolab's like, you're good. You got that incorrect solution correctly labeled as incorrect because you have a single test case that says it's incorrect. That's enough. That's all it takes is one. So on that side of things, with the incorrect solutions, you're demanding perfection from the incorrect solutions. Just have one test case that fails them, and you'll be good on each one of the incorrect. Once you get past all the incorrect solutions, once you have enough testing to pass them, which I always maintain shouldn't be too much. It is, don't get me wrong, you will spend time on those, most of you will. But if you're sitting down thinking of your test cases, thinking of your common cases, your uncommon cases, your edge cases, getting a nice variety of test cases, and really sitting down and writing a really solid test class with lots of test cases, you shouldn't really have to worry about those incorrect solutions. You should just automatically be knocking all those out. Most students, when they're not, it's because they're half-assing the tests. They write like one test case and submit and just hope it goes well, and then they add like one test case, submit again. If you just sit down and write a good test class, I don't think the incorrect solutions should be all that tough. Now that said, every once in a while there is a very slippery incorrect solution that's very evasive from your tests that causes frustration. I try to avoid that, but every once in a while I get one that's just pretty hard to get, a pretty strange edge case. I'll try to avoid that these days, but I have had those in the past. Once your tests are good, then finally Autolab will run the tests that are on Autolab against your code. And then if you pass that, then you're finally done with that task. So this is true for task 1. This won't be true for most tasks. Most tasks will either be testing tasks or programming tasks. So you have either this part that's on the screen or just running tests against your code. But task 1 is like a full autograder. Go through all 3 phases of grading: the correct solution, incorrect solution, and running tests against your code. So you get to see all 3 phases right from task 1. If your tests pass in AutoLab, you're good on the correct solution, you're good on all the incorrect solutions. It doesn't necessarily mean your testing is complete or robust or thorough. It just means that it was enough to pass AutoLab. It was just enough to reject those specific incorrect solutions. So there are some cases where your tests will be good, you'll be passing, your code will be passing your tests, but you still won't pass the tests in AutoLab, that third phase. It's fairly rare, but it does happen a bit if you kind of half-assed the test but still got by AutoLab with broken code and tests that weren't thorough. So just a word of caution with that. But except in those cases, if you're sitting down writing a really good test class, the third phase should be automatic. If you're passing your tests, you should just get past that one. All right, any questions on this? Yeah.
Curiosity, how do you tell when two doubles are going to return the truncation error?
You don't. So the question, when do you know two doubles are going to return the truncation error? The short answer is you don't. You just always have to be prepared for it. So if you're always using compared doubles and always allowing some tolerance, you don't have to worry about it. There are ways to know, but it depends on understanding the double representation and then actually figuring out when the truncation errors will happen. But for 116, we're just always going to assume there are truncation errors. But that's a deeper topic for, I think 220 will start touching on that. But it's a tough one to detect. And it does, in your career, looking forward and everything, it is always something you should have in the back of your mind because there are some cases where that will, really mess up your program. If those compounding errors, if those truncation errors compound enough, it can mess with not just your testing, but actually the logic of your program. So we have to be careful of that. But it's a big, deep question of how to know that's happening in your code. Okay, let's move on. So let's get into today's content. 27 minutes in, we should be able to do this still. We did good on the last lecture. We got through everything. I have this method, similar to the method on Wednesday. It's a very simple method, but I want to use this to show new concepts. This method should add two numbers. That's it. That's all it does is add two numbers. Except this one, you might not be able to read this code. So this is going to be our first recursive method. We have a method calling itself. We'll talk about that a lot more when we get to the slides. But for now, this is a method that I claim adds two values, and I claim that it works. It does what it's supposed to do. But how do you believe me? Should you believe me? Should you believe me that this actually returns the addition of a plus b? Well, how do we actually know that? We can run the main method. I wrote a little main method. It adds 4 and 3. I run it, and if it ever gets through here, it does return 7. But how do we really get confident that this is correct? Well, you should all know where this is going. We're going to write some tests. So let's write some tests so you don't have to just take it for my word that, oh yeah, it works, trust me. Let's write some tests and actually verify that it does work. So to write tests, and mostly because I want another example of tests. So let's write some tests. Public, void, no static on tests, test, add, and I'm going to annotate this as a test. And I'm just going to use one-line tests here, assert true, and I'm going to do adder.add, call my method. Make sure whenever you're testing that you call your method and take the return value and test that return value. For some reason, it's a pretty common mistake I see. I think it's just when you're first getting used to testing that someone will either not call the method they're testing at all or call the method they're testing but never assert the return value. So don't fall into either of those traps. And let's add... Why is that in red? Let's add 2 and 2, and we expect this to be, what am I doing? We expect this to equal 4. So we're going to assert true. We expect this to return 4. These are ints, not doubles, so we can safely use equal, equal. And we're going to make sure that that equals 4. and it's because it's first recursion. First recursion.add. So we're going to make sure that that returns 4, and it's our first test case. Then we're feeling decent if we pass that, but not great. So let's think of some more test cases. Oh, I did this wrong. And we can add some more test cases here. I'll just come up with some. I'm going to try to do my math correctly. I did that backwards again. When I'm doing a lot of test cases, I like to remove all the parameters. Just keeps it a little simpler when I'm writing code. Oops. 1, 5. Oh, my goodness. Keep hitting my thing. 1 and 5 should be 6. I want to make sure that this also works in reverse. My method should work no matter the order of the parameters. So 5 and 1 should also be 6. Let's do 10 and 20. Should be 30. How about 14 and 207? Why do I make the math so hard on myself? 1, 2, 221, is that right? And, I don't know, 8 and 9 should be 17. So we got some test cases here. We should be feeling decently confident in the code if these test cases pass. But these are only what I would call the common test cases. And it's going to follow pretty similar to last lecture. These would be my common test cases. So I'm going to name my method test add common. But I want to think of all of the bugs that can happen with this code. What's everything that could go wrong with this code? Well, let's make sure we get some negative values in here. We'll test the uncommon, where we're getting a little trickier with our tests. We want to try to trap our code. When you're writing test cases, when I write test cases at least, I like to think, how am I going to trick my code? How am I going to really challenge my code, really put it to the test, and make sure that it's doing what it's supposed to be doing? Well, let's try 2 negative values. Let's try the first argument being negative, second one being positive, first one being positive, second one being negative. These are 2 different situations. I can imagine people writing an add method that doesn't commute. So let's make that. Well, it's not really the same thing what I just said. But anyway, 3 and negative 3. And I would write more there, but I don't know. I don't want to take up too much lecture time just thinking of different test cases. So let's get on to also our edge cases. So our edge cases for this, just way too parallel to the last lecture, I guess. But my edge cases are going to be anything involving 0. So 0 plus 0 better be 0. 5 plus 0 better be 5. And I want to make sure this does commute, actual commutative right there. 0 plus 5 also equals 5. So I got a good test suite. I think if the code passes all of these test cases, we should feel pretty good. Like I said, I would add more negative ones here if I were really testing this to make sure the code is solidly robust. But for a good starting test case, I mean, I'd only add a couple more here. Add some large values would be another thing. But this, I'll feel pretty good about the code if all this passes. I want to go up to the class, run the entire class, and see if my code passes. Does that actually add 2 values? Let's see. And did I write all my test cases right? In the last lecture, I didn't do my math right on one of the test cases, and it broke. And I'm feeling good. All right, we got a bunch of green check marks. And one thing with my tests, I do like to break my code. And I always want to see my tests fail. This is something I personally like to do. A lot of devs like to do this. I shouldn't say me personally. I like to see my tests fail on incorrect code to make sure that my tests are actually testing something. For example, if I did forget to call my method, or if I'm not actually testing the value of my method, or I have a bunch of copy-paste errors and I'm not actually testing anything on accident, I want to make sure I don't have any of those bugs. So my test did fail. I should fail the first test case in every situation. And I could have my hint text here to give me some information, what actually was outputted. For the sake of time, I'm not going to do all of that. but my tests fail on incorrect code and pass on correct code. So I'm feeling pretty good that this is testing my code and that this method is actually adding two values properly. I showed this in the last lecture, so I might as well show it right here. Let's say I have 90,000 here. 90,008. This test case actually will fail. It won't even fail. The program's going to crash before it even gets there. And when we get to the slides, which is right now, we're going to talk about why. I got myself a Stack Overflow error. Oh, crap. Look at that. Let's see what's going on with that. Okay, any questions on the tests for this before I get into the slides where I want to explain how this method actually works? Everyone feeling good about writing tests? And we haven't had an example in class yet, but for your homework, like I was mentioning earlier, when you need to test a method that takes an array list or hash map, you'll take the content from that lecture, mash it in with the content from these testing lectures, create an array list or hash map, add a bunch of values to it, and that's your input. Call your method with that input and check the output to make sure it's what you expect. Whereas here I'm just testing ints. For your homework, you would say new array list, and then call average with that array list. All right, let's talk about recursion. Recursion is when a method or a function, or in general, whenever something refers to itself. Recursion is when a method or function calls itself. So a recursive method is a method that calls itself. This method calls itself. So we're defining a method named add. And inside the definition of that method, we're calling a method named add. This method calls itself. This method, in the definition of the method, its own definition depends on its own definition. We can't finish writing this method without the method already being written. It's a weird concept at first. We're going to explain it. We're going to see how this actually works, how a method can possibly call itself. So this is a recursive method. It's only a recursive method if it calls itself. It has to call itself. That's what a recursive method is. It's a method that calls itself. Did I say that enough times? It's a method that calls itself. So let's see how this works with a memory diagram. Woo! So I think this is a lot easier to see how recursion works with a memory diagram. I can explain it and try to explain the concept in slides, but with a memory diagram, it's just right there in your face. You'll see exactly how this works. So starts like any other memory diagram. We start with a method call in this case. We put our stack frame on the stack. We assign the parameters, the values of the arguments, put those inside the stack frame, label the stack frame with the name of the method call, and have our return arrow go into wherever the value is going to go. In this case, a variable that we're going to put on the stack with no value. So all that should be feeling pretty similar, pretty familiar at this point. It's been, say, Friday, 5 lectures? No, we didn't do memory diagrams last time. The 4th lecture where you've seen a method call, I believe we had method calls in all the other ones. I might be wrong. At least 3. So this should be feeling pretty familiar, putting method calls on the stack. It's a new thing. Last week it was, but I assume you're getting pretty comfortable with this. If not, feel free to ask questions. I'll talk about that. But I think I can do all that in one slide at this point. Should be feeling pretty familiar. And then we get to the recursive call. The first condition is false, the second condition is true. We get to this return add of a plus 1, b minus 1. And this is our recursive call. Let's get to the good stuff, the new stuff. The trick with reaching a recursive call, and whenever we have to call the method itself, is that there is no trick. You just call the method. Just like any other method call, you just call the method. So we're going to put another stack frame on the stack. This is a little new because we haven't seen multiple stack frames on the stack before, but we're going to add another frame to the top of the stack for the method call. Just like this method call. We hit a method call. We put a frame on the stack, assign the parameters equal to the values of the arguments, and then start running the code of that method call. So we called the method from this stack. So the question is, what's the value of A and B? Well, we called it from this stack, and we got A plus 1. So the first argument is going to be 5, and B minus 1, 3 minus 1, the second argument is going to be 2. So when we create the new stack frame, we're resolving these expressions to their values based on A and B from this stack frame, the stack frame that was running when the method was called. And then when we create the new stack frame, it gets the new methods that the new arguments that we just evaluated as its parameters. So the A and B in this stack frame are going to be 5 and 2 because that's what they evaluated to when we called the method. So we hit a method call, we put another stack frame on the stack, we got the parameters assigned to the arguments, we got the name of the method, and the new thing is the return arrow. Whenever we have a return arrow, it points to wherever the return value is going. We're not storing this value in a variable, so we're going to just point it to the stack frame that called it. So whenever this returns, it's going to return its value into this stack frame, so we just have the arrow point to that stack frame. And we just keep going. We just trace through the code line by line like we're an interpreter. And we just blindly follow what the code's doing. That's exactly what the computer's going to do, what the JVM is going to do when it runs your code. It's going to go through your code and just call, it sees a method call. That's a frame on the stack. So we're going to do it again. Get another frame on the stack. This time A and B were from this frame, 5 plus 1, 2 minus 1. So A and B are 6 and 1 for this stack frame. And notice that we have 3 frames on the stack at this point. Only the frame on the top of the stack is active. These other 2 frames are just sitting there waiting for their return values, waiting for this method call to resolve to a value. And for that to happen, all the other stack frames have to return to get back to that one. And then the main stack frame is just sitting there waiting right here for this to resolve to a value before it can move on with its thing. So we have 4 frames on the stack. Only one of them can be active, whatever's on the top of the stack. And the frame on the top of the stack is visually in our memory diagrams the frame on the bottom of our diagram. So this is the top of the stack. This is the only active frame. So the question of what's A and B? What's A and B at this moment? Well, we look at the top of the stack. A is 6, B is 1. Even though we have 3 A's and 3 B's in stack memory, only the ones within the currently running stack frame are available to us. We can't cross these solid lines. 6 and 1, these are the values of A and B at this point in time. Now, in other stack frames, we do have other values for A and B, but they're not currently active. They're not in scope right now. We call the method again. A plus 1 is 7, B minus 1 is 0. This is the new active stack frame. We call the method again. And finally, we get something a little different happening. We hit what's called our base case of the recursion. This is a situation where we have a method call of a recursive method that doesn't call itself. So we're going to hit our base case of B equals 0. B is 0, and we're just going to return A. So we return A, remove that stack frame from memory, we pop it off the stack, and then whatever is the next stack frame, this stack frame regains control and gets the return value 7 from this stack frame that just returned. So return 7, the stack frame on the top of the stack now was waiting for this call to resolve. That call resolved to 7. And it's just going to return it. It's not going to do anything with it, but return it to the next stack frame. So that call of add of 6, 1, return 7. Return it. This stack frame gets control again. It gets the value 7. It says Cool. Well, I'm done with my stuff. I'm just going to return it. This stack frame was sitting there waiting for add of 4, 3 to resolve. No, it was waiting for add of 5, 2 to resolve. 5, 2 resolved to 7. It's going to return that back to the main stack frame. And the main stack frame was waiting for add of 4, 3 to resolve from this stack frame. That stack frame returns 7, store 7 in result, print 7 to the screen. And we have our first successful recursion memory diagram. So we just treated these recursive calls as any other method call. And we can see how when we go down the recursion, as I call it, going down the recursion, when we're adding frames to the stack, we're updating the values of the parameters. And then when we get to the base case, we're going to start returning back up the recursion and returning the value back to the main method, which successfully added 4 plus 3. Now notice that we get a lot of frames on the stack with this method. And when we start our program, we get a chunk of memory, which is going to be our stack space. And it's a finite, fixed chunk of memory. If we have too many stack frames here, we're going to get that stack overflow error that we saw in the code when we were in IntelliJ. If we run out of stack space, that's a stack overflow error. We just don't have any more stack space left. The most common way for this to happen is to never hit your base case. If every call to add added another stack frame to add, we would have what's called infinite recursion, and we're eventually going to run out of stack space and crash the program. So we always have to reach our base case eventually, some call of the method that doesn't make a recursive call. We will revisit recursion multiple times through the semester. This is just your first little taste of recursion. And it'll be a while before we expect you to write recursive methods. So if that's confusing or not, we will revisit that often throughout the semester. And quickly, I want to talk about interpretation versus compilation. I never know where to put this. Paul visits this on day 1 during syllabus day. So I'm finally getting this in somewhere. Interpretation versus compilation. So interpretation, this is when code is, maybe I won't get to it today. This is when code is executed one line at a time. Compilation is when your code is translated into another program and then executed. Python and JavaScript were interpreted. This means if you have errors, they're usually runtime errors because it just jumps in and runs your code until if something wrong happens, it just says, I can't do this. When you run your program, it'll run immediately. Java, among other languages, are compiled languages, meaning it's translated into another language before it's executed. So you have compiler errors. The compiler, when it's trying to translate into another language, it'll have errors and let you know right away before the program ever runs. What the difference it'll make to us, the practical difference, among other things, is that when you run a Java program, you see that progress bar on the bottom of IntelliJ, and it takes a while before your program actually runs. Java is compiled into Java bytecode, which runs on the JVM, which is more commonly just called Java. If you've ever seen this pop up to update Java, that's your JVM. My music's driving me nuts. It won't start. It does say